All right, so this should be a pretty quick video, just kind of continuing off the last video, which was really long, talked about vector spaces and subspaces, and I figured that it'd be a good idea to talk about a few more examples of things that make up subspaces and what subspaces kind of look like visually, and also to just cover a little bit of notation. So last time I talked about this idea of a subset. And a subset is, visually was the idea that if I have a collection of items in this space V, or in this, we'll just call it a set, not a space V, a subset could be any smaller collection inside of it, but a subset could also be the entire thing, right? So it's basically just a collection of the items that are inside V itself. And we denote this, we say if we take a collection of things H, the notation is that H is a subset of V. So this notation here, it's kind of like the less than or equal to sign, except in set notation, we kind of use this sideways U. And the reason why there's this little bar underneath is just like the less than or equal to sign. It indicates that I could have, in theory, picked everything inside of V here. If you wanted to talk about, if you want to say that H is what we call a strict subset of V, then there wouldn't be the little underline thing. We would just write this. So that's notation for the word subset. So sometimes in the textbook, instead of saying, oh, suppose that H is a subset of V, they'll just write one of these notations, and then they'll say, show that H is a subspace, or prove that it is not a subspace. So that's just a little bit of notation to kind of add to your notes. So I want to talk about some things that maybe aren't super obvious that they might be subspaces. So this is just going to be examples of subspaces. All right, examples of subspaces. So for example, last time we introduced the polynomial space and said, if P sub n, if the polynomial space consisting of nth degree polynomials is itself a vector space, then all of the, well, we didn't prove it for all of them, but we showed that P1 is a subspace of P2, and the chain continues if you really wanted to do it. But one example of something is that if we let H be equal to just the zero vector, if H is just the zero vector, and V is a vector space, and H is clearly a subset of V, because by definition, if V is a vector space, 0 is in that vector space. And it turns out that H here is a subspace. So it turns out then H is a subspace. Right, and if you remember the three criteria for being a subspace, we have to have the zero vector, which it's right there, it's the only thing in our set. We have to be closed under scalar multiplication. Well, if I take, any C times the zero vector, I'm just going to get the zero vector, and this holds true for all C in the set of real numbers, so that's true. And since we need to be closed under vector addition, but the only vectors that's in here is 0, so if I take 0, the 0 vector plus the 0 vector, I get the 0 vector, so I don't leave H. So it turns out that that the 0 vector is itself a subspace, and this one's kind of pretty easy to think of. Here's an interesting one. So for example, is R2 a subspace of R3? Okay, and you might think that, well, if I draw R3, right, this is R3, you're like, R2 is just down here, right? It's inside of it. So R2 is first off, we need R2 to be a subset of R3. So the question is, the first thing we have to ask is R2, is this a subset of R3? And a lot of people would say yes, but I'm here to tell you that you're wrong. R2 is not a subset of R3, and the reason is because by definition, all of the elements in R2 are vectors with two components. You have an x and y component. And all of the elements in R3 are vectors that have three components. These are clearly impossible to be in the same space because by definition, the ones in R2 have two pieces, the one in R3 have three pieces. So it turns out that R2 is not a subspace of R3, but we can kind of get around that caveat because it turns out that, but the set of all vectors x, y, 0 that are, in R3, and then such that x and y are just real numbers. This set is definitely a subset of R3 because all of the vectors that we're getting are from R3. Is the 0 vector in there? Absolutely, because we're considering for all x and all y in the set of real numbers. So clearly the 0 vector is in there. So if you were running through your checks. Is this closed under vector addition? Sure, if you take some x1, y1, 0, and you add some x2, y2, 0, you're going to get something else. Let's call it C1 and C2, 0 on the top. And this is definitely, it fits the criteria of being in this space. So that works as well. Are we closed under scalar multiplication? Absolutely. If you take C and you multiply it by x, y, 0, you're just going to get something else. You're going to get a new, again, maybe I'll call it H1 and H2, 0, right? You're just going to get C times X, which is a new number, C times Y, which is a new number, and this is it's in this set right here that I just defined, and that is the XY plane, right? That is affectionately the XY plane. Okay, so that's kind of an interesting one that kind of fools people sometimes. And one thing that you might notice is that, if the more you do this, and the more you start working with subspaces, you will notice that something can only be a subspace if when I sketch a picture of it, it goes through the origin. Okay, like it has no chance of being a subspace if it doesn't go through the origin. So for instance, the XY plane here, right? This plane, which is kind of defined by that set over there, that plane goes to the origin, so it has a chance of being a subspace. Not guaranteed, but there's a chance. However, this plane right here doesn't go through the origin. It immediately fails being a subspace because the 0 vector is not in there. So we need to include the 0 vector. So visually, if you're asked a question and it's like, hey, is this a subspace? One of the easiest checks to do is like, all right, if I draw this thing, does it go through the origin? Another thing that's probably the most important reason why I'm making this video is just an example, and it's going to be given if I give you, let's say, two vectors v1 and v2 in some vector space v. So this has to be given to you that this is a vector space, and it's going to be assumed that big V represents a vector space, but I'll write it down anyways. So given this, I'm going to show that H equals, so this subset, right? This subset, the subset that consists of the span of V1 and V2 is a subspace. It's a subspace of V. And the idea being that what we're going to do is we're going to show that if you take that it turns out this is just supposed to kind of be a little bit of an inkling or a guidance to say that, it turns out that the span of any collection of vectors, whether it's one of them, two of them, a billion of them, whatever, the span will always give you a subspace. And that is a very important thing that we're going to use later in the class. But, if you think about it visually, right, without doing any like actual algebra yet, right? If I take two vectors, okay, v1 and v2, let's say for the sake of example that this is just R3, okay? R3, it's a vector space, great. I take two vectors in there, one vector right here, take another vector over there. The span of them creates what? Well, if they're linearly independent, their span is going to create a plane, right? It's going to, just going to do this and that, and it's going to expand and just be a whole plane. And most importantly, it's a plane through the origin because, 0 times v1 plus 0 times v2 is equal to the 0 vector, and that is that's clearly inside of H. So therefore, we satisfy the first check of being a subspace. Now, if you just think about it, the whole point of being a subspace is that we have picked a collection of values. We've picked a collection of values that when I add other vectors that are in that space, they don't leave, okay? And the idea being that, look, if you're on a plane, this is just like some intuition. If I pick another vector on this plane and I add it to this pink vector, it's going to give me a new vector that is also on the plane. I can't, because these vectors are all coplanar, they all share that kind of commonality, which is the direction of the plane, right? I can't add two vectors and magically get one that's sticking out at a 90-degree angle to this plane or something like that. So the idea that if I take some vector v1 and I add it to some vector v2, that result is still going to be on this plane, right? It's in the span of v1 and v2, and this, of course, is very easy just to think about now algebraically, because for the coefficients, x1 is equal to 1 and x2 is equal to 1, right? By definition, this is definitely in the span. So we've satisfied the first criteria, the second criteria. The third one is almost laughable because, if you take take any vector, so you say let v1 or let's let w be some vector in H, then c times w, right? Just think about it. If I take any vector w and I multiply it by some multiple c, it's just going to stretch it out along that same plane. It's still going to be there, right? And sure enough, right, this is going to be in the span. This is going to be in the span of v1 and v2, because w, now how do you show this algebraically? Well, if w is in H, that means that there exists some x1 v1 plus x2 v2 that equals w, right? So if I multiply everything, if I multiply both sides by c, and I multiply this by c, then on the right side I get cw, and on the left side I'm just going to get c times x1. It's going to create, I don't know, let's call it y1 v1, and then it's going to create a y2 v2, and this is definitely of the form of something in the span, and so we have successfully shown this, right? So it kind of makes sense, right? Even if you had one vector, even if we were just asking, does the span of just one vector, is that a subspace? Absolutely. It's a line going through the origin. It goes forever and ever and ever. It's impossible to deviate from that line. So spans are also subspaces, which is going to be kind of a pretty interesting thing. And on that note, I think we'll just do one more example and then call it. So for example, let's see, let's let H be the set of all vectors of the form, let's see here, of the form a minus 3b, b minus a, and then b. Let me make this a little longer. Okay, so H is the set of all of these vectors where a and b are from the set of real numbers, and so the technical way of shorthanding everything that I just wrote here in math or in set notation, we would say let H be the set of all these vectors a minus of all the vectors b minus a and b from R4 such that a and b are real numbers, and our goal is to show that H is a subspace of R4. Okay, and this actually turns out to be pretty simple, even though this is kind of weird because, like, dang, I have a bazillion vectors, right? I have a whole bunch, and to show to show that this thing is a subspace, I need to show the 0 vectors in it, which actually is pretty easy. You can kind of see it just by setting A and B equal to 0. So that's 0 is definitely in there. Showing that this is closed under vector addition means you would have to do let U and V be 2 vectors in H. You would have to write them in their general notation, add them, and then show that the result still looks like this. And the same thing for scalar multiplication. But if you use the idea, right, that we just covered, which is that the span of something is itself immediately a vector space, I can take this and I can rewrite that vector. I can put everything with an A and 1, right? A, negative A, 0, plus, right? It is the same thing to take that and write this, right? This is the same thing as this single combined vector notation. And I can factor out an A from the first one, 1, negative 1, 1, 0. And I can factor out a B from the second one, negative 3, 1, 0, 1. And this is the span. This is the span of 2 vectors. This is the span of 1, negative 1, 1, 0. And also the vector negative 3, 1, 0, 1. And so since this is the span of 2 vectors, and these vectors are from, those vectors themselves are in R4, this implies just basically on the, via the work that we did before, that then this just immediately gives you that H is a subspace of R4. And I really wish there was some notation for the word subspace. There isn't notation, at least that I'm aware of, that kind of commonly represents subspace. So you just write it out. And then you're done. A little square box indicate that you're done. All right, so that was just a little continuation of subspaces, giving you some, insight as to some of the nuances of when things are and aren't subspaces. I was showing you a little bit more practice of just kind of, how you can kind of think about these things geometrically, like by drawing pictures, how you can do them algebraically. In the algebraic ways, I kind of rushed through a few of them because the goal of this video was less about that, because that's what I focused on in the last video, was the rigor, and more on just trying to get through some various different examples here. But when you want to show it for your homework, you do actually have to do the rigor and kind of show the different steps, unless, you get something like this, and if you get something that's just like, hey, show that this is a subspace, and you show that it's a span, then you're good to go. So that's going to do it. The next video is going to cover some very special subspaces that we are interested in looking at. So there might be like 1 or 2 videos for this week, and then we'll call it good. So hopefully you're finding this stuff interesting. This is all just pure theory. And if so, head to the next video. And if not, that sucks. Head to the next video anyways.